Okay, welcome back, and we have just said that the pressure of a gas is related to its volume and the number of air molecules inside the gas and its temperature by this formula here, where K is a constant. This is the one that physics people like to use. However, chemistry people don't like to use this form of the formula. So instead, they like to use PV. So this is exactly the same as the physics version of it, but instead of the number of air molecules, they like to use the number of moles of air that are in there. And then there is a constant, R, that goes with this version of the formula, and then they still use the temperature, T, in Kelvin. So what do we mean by a mole? So 1 mole of anything is going to be equal to approximately 6 times 10 to the 23rd of something. So if you have 1 mole of oxygen, then you have 6 times 10 to the 23rd molecules of oxygen. If you have 1 mole of bananas, then that means that you've got 6 times 10 to the 23rd bananas. That's a big number. That's a lot of bananas. And the reason why they do this is because in chemistry, you have to measure huge numbers of atoms. So like in just a teaspoon of sugar, there are many atoms of sugar in there, or molecules of sugar. So instead of measuring every single one of those molecules, they measure a whole bunch of them at one time. And so that's what the mole is going to be. So this is the version of the formula that chemists like to use. But we're not, because we're physics people. So we don't like using chemistry stuff in here. So I'm going to get rid of this, and then this is going to be our equation that we're going to be working with. Okay, now one application of this formula is to be able to compare the initial values of the pressure, the volume, the N, and the T with the final values. So let's say that you got this blob of air which has a certain pressure P, and now it's useful to think about the pressure as being applied to the gas like that, and then it's going to have a certain number of molecules in there, so that's the N, and then it's going to have a certain temperature T, and then this blob has a certain volume V. So this is how we would symbolize it. Now, let's say that we change it. Maybe we squeeze it. So if we were to squeeze it, then it's going to have a smaller volume. So the volume is going to change. Now, maybe we want to know, if we squeeze this thing, how is that going to change the pressure? Or how is it going to change the number of air molecules? Or how is it going to change the temperature? So we would like to be able to compare the before with the after. And so the way that we can do this is to write the equation 2 times. So that we're going to write the equation P initial, V initial, N initial, T initial. So that is what you start with. And then rewrite the equation, but this time put F's. So this is going to be the final pressure, the final volume, and so forth. Now, what would happen if we solve each of these equations for the letter K? So if I want this K to be on this side over here, then it's going to be PV over NT, where this would be P initial, 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 and initial. And then let's do it again for the final. So then over here, we could say this is equal to pressure final, 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 final. And then we set them equal to each other. And then we end up with that the pressure initial, the volume initial, divided by the N initial, temperature initial, is equal to the pressure final, the volume final, the N final, the T final. And now you're saying, well, that's worse than my original equation here. Well, it's a useful equation because now we can compare what were the initial conditions of the gas to the final conditions of the gas. So let's actually apply that here. Now, let's, instead of changing all of the variables, let's let some of them be constant. So again, let's say that you have this blob of gas, and we're going to change the blob so that the volume is going to change. So the number of air molecules, let's say 4, is exactly the same as initial and then final. So the N did not change. And then let's also assume that we don't change the temperature. So whatever the temperature, maybe this is room temperature, is the same as this temperature over here. So if we go back to this equation and we don't change the N and we don't change the T, then notice that the N and the T are exactly the same on both sides of the equation. That means we could cancel them. So then that would mean that you end up with that just PV equals PV. And so that's one version of the formula if N and T are held constant. Now I'll let you do the derivation for the other two. So begin with equation 12.3, and then this time don't change the N and don't change the P, and then you end up with that V over T equals V over T. And then another version of the formula is going to be, well, what happens if the P and the N don't change? Then it turns out that the volume and the temperature are going to change according to equation 12.43. And there are other variations. So there are more than just these three. It just depends on which variables that you want to hold constant. Okay, so let's do a sample question here. If the temperature of a gas triples, and you're not going to change the pressure of the gas, and you're not going to change the number of air molecules, what would have to happen to its volume? And so we say to ourselves, if P and N are constant, then that means that we're going to be using version 3 there, 12.4c, V over T equals V over T. Okay, now we're going to substitute in for the final temperature 3 times the initial temperature, because it says what would happen if the temperature tripled. So instead of T final, we're going to put in 3 times T initial and then simplify. So notice that the T initials cancel, and so we're left with that the final temperature is going to be equal to 3 times the initial temperature. Okay, so this is a nice way of solving gas problems. Now you can verify that this is true by taking a balloon and then blowing it up, okay, and then tying it off, and then put it in your refrigerator and see what happens. So what happens to the temperature of the balloon if you put it in the refrigerator? The temperature goes down. And when you take out that balloon the next day, you will notice that that balloon has shrunk. It got smaller. So as the temperature went down, so did the volume. If the temperature goes up, so does the volume. The balloon would expand. Because remember, we didn't change the N because it's got the same number of air molecules inside the balloon because we tied it off. It's at the same pressure because we are at atmospheric pressure. So the pressure pushing in on the balloon is 1 atmosphere of pressure. And then the pressure inside is going to be the same. So the two are in equilibrium with each other. Okay, let's take a break, and then when we come back, let's do another sample question using the ideal gas law.